Okay, it is now 12:01. We're going to go ahead and get started. I'm Michael McClellan. I'm one of the partners at L3 Levine Electronics and Electrics. And today we're going to be talking about ways to save money and really space in the electrical room. A couple housekeeping items before we get started. This is a GoToWebinar, so your phones are muted. But we would love for you to ask questions and interact with us. If you could please use the buttons to the right, there is a question button where you can ask questions. You'll also find a few handouts. I believe I included a copy of this presentation, a few drawings from one of our manufacturers, and there might even be a marketing brochure in there. With me, I have my longtime colleague, Adam Norrell, who has a lot of switchgear experience as well, and Mike Bukovitz, who's also been around switchgear his whole life.
Since electricity was invented.
Yes. Okay. So if we're going to talk about size and saving space, we're going to come up with a sample electrical room, and it's meant to model, any medium-sized industrial facility, or maybe even a water treatment plant. And it's going to look like this. Your typical water treatment plant or industrial is going to have a lineup somewhere of medium voltage switchgear. They're going to be served from the utility at 12,470 or 13.8 or whatever. And they're going to have obviously this lineup of medium voltage switchgear. Then they're going to feed unit substations over here to the lower right with somehow feed it with the medium voltage breakers. And a very popular scheme nowadays is to use two breakers in the medium voltage switchgear to create a loop system. So that's what we've done. And then we have our unit substations daisy chained together. And if you do this, you're also going to require some loop switches on the transformer. And some people call those transformer disconnects. Then you can see over here to the right, we have a transformer. Let's see if I have a pointer here. You can see over here we have a transformer, and then a lineup with a main breaker that feeds some medium voltage motor control. So perhaps we have some medium voltage chillers or medium voltage pumps. We have one 1200 horsepower, one 800, and two that are 200 horsepower. And based on input from our client, the 200s are fed from a direct across the line contactors. The 800 is fed with a reduced voltage starter, and the 1200 is fed with a medium voltage VFD. Okay, so this is what a plan view of what our electrical room might look like based on the one line that we were just studying. We have a lineup of medium voltage switchgear here, and many sections of medium voltage gear are 36 inches wide. We have a transformer, our 3000 kVA, that's transforming, say, 12,470 to 4160 for our medium voltage motor controls. And over here we have one of the unit substations. Now, the first item we're going to take a look at to try to see if we can't save some space are the transformer disconnects. And I've highlighted them here on the drawing. And we're going to use a mechanism that I stumbled across about 7, maybe 8 years ago when we did a project with Siemens. And it was actually for the Gigafactory out in Nevada, not far from Las Vegas. And we used a 35 kV mechanism in that case, and those sections were only 20 inches wide. And let's take a look at what our typical transformer disconnect would look like if it's air insulated. That unit is going to be 36 to 38 inches wide, and is also going to need a cable transition section to connect to the transformer, to translate the bus so that it can connect to the transformer. whether it's liquid or dry. And so that ends up being around 56 inches in linear width. And it's metal enclosed gear, so it's going to be around 72 deep. There are cases where we can get it less than that. So here's the switch that I'm talking about. This is a mechanism that we purchased from Schneider. It's called the HVLCC. And what you're looking at in this slide is a configuration of three pole switches. And maybe some of you are asking, why do I need 3 switches for a transformer? Well, if you have a loop system, you always want to be able to have an open point in that loop. So one of those switches is going to need to be open. And if you, for any reason, need to change the open point because of a fault, you want to be able to open and close those switches. Additionally, you want to be able to loop through a de-energized transformer. If you need to work on the 480 volt side of that transformer, you can turn off the switch that feeds the transformer while keeping the other 2 on, and that will enable you to continue, you have continuity in your loop, and then you can work on the 480 volt side of that transformer and ensure that the transformer is dead via the visible disconnect available in this switch. Mike Bukovitz, you're familiar with this switch. Would you like to comment?
Absolutely. Other benefits of this switch, in addition to the obvious real estate space savings that you can see from these drawings, are that there are, and you have to look in the middle of the switch, you can actually see it in Michael's drawings, 2 little circles. If you look in the switch mechanism itself, it's on the left-hand side centered. Those are arc-rated viewing windows. So the top window shows visible confirmation of grounding, and the bottom window shows visible confirmation of phase blade disconnect. So we have visible confirmation of blade disconnect and visible confirmation of grounding. And that leads to the last point here, which is that this can be ordered as a 3-position switch, closed, open, and grounded. So an integrated arc-safe grounding switch. So that the mechanism itself is arc-safe, so it can be switched up from the outside, enclosed, energized, without any arc-rated PPE requirements, which of course is a maintenance advantage in many situations. But for anyone who has not experienced integrated grounding, anytime you can sell this to your customers or use it yourself, there is no going back. When Europeans come here and they see us with new equipment, getting out our grounding cables and our PPE and attaching with our hands to ground, and then with a hot stick, one at a time, attaching clamps to the phases, and both from the safety risk and the time and effort involved, they think we're barbarians because integrated grounding has been a requirement in new medium voltage equipment in Europe for the last 20 years. But that is not a requirement in IEC land, but I'll tell you, it is sure a convenience and a very effective safety solution as well. So it meets all the requirements of NFPA 70E Article 120.5 for visible confirmation of blade disconnect and visible confirmation of grounding. So thank you, Michael.
Great, Mike, thank you. So in addition to all those benefits, let's look and see how we did. We took 3 sections of metal enclosed primary switch gear and plus the transition section, which came out to be about 126 linear inches. And we converted all that with the same functionality, actually more functionality, with the grounding, integral grounding switches, And I believe these also include live line indicators. Is that correct, Mike?
Yeah, they're available with both line and load side indicators, but this is key. Those line and load side indicators are rated for supplemental verification, so they're useful, and I do use them. But we need to be clear that does not replace absence of voltage verification, again, as required by Article 120.5 and NFPA 70E.
Okay, great. So you can see the results here. I've tried to make it clear. We've gone from 126 linear inches to 59 inches without giving up any functionality at all. And the way we've done it, just some of you are probably curious as to, well, how do you fit, a dozen eggs in, one egg cup. These switches to the left that are air insulated, they are phase A, B, C from left to right. And the interrupting mechanism is an air interrupting mechanism. Over here to the right, the HVLCC, the phases are A, B, C front to rear, and the interrupting mechanism is a SF6 hermetically sealed device, which has been proven over, I think this has been in existence for 25 years. So let's see what we've done to our room. We really have made some progress here. Over here down at the bottom left, we've converted this to 16-inch sections, and we still have our 3 load break switches. So moving on, the next item we're going to look at is the medium voltage switchgear. And there's lots of different options here. In the last 15 to 20 years, there has been some pretty good innovation in the world of medium voltage switchgear. At first, let's take a look at what is the old standby, which has been around forever, and this is what we call metal-clad switchgear. Medium voltage metal-clad switchgear. And it was invented and standardized around the same time as the vacuum breaker was invented. And it is a very robust system. It is also very particular in its standard. The metal-clad standard tells the manufacturer how to build the medium voltage gear. It does not leave any leeway for where the horizontal bus goes. And if you can see in this drawing that this is where the horizontal bus is here. Okay. The horizontal bus has to be barriered, and it has to run through the center of the gear. That has to be barriered from this rear section, which is the cable compartment. And the bus also has to be barriered from the breaker compartment. They have to be 3 individual barriered compartments. And you can't get this done in less than 94 inches. 94 inches is how deep metal-clad switchgear is, period. So let's look at some other ideas. Okay, let's look at metal enclosed gear. The metal enclosed standard governs medium voltage switchgear. We think of it a lot when we mention primary switches, air insulated primary switches, but it also includes breakers. The rules governing metal enclosed switchgear are not related to construction. They are only related to testing. And let's look at some ways in which some manufacturers have used this to save cost. So right off the bat, we've gone from 94 inches to 72. So this is still rear connected. This is still 36-inch wide gear, but now we've reduced the depth by taking some of those barriers away to 72 inches. And there's many manufacturers who can do this safely and easily. One of the other solutions is front connected medium voltage switchgear. And the main advantage to this, especially in a block building, you sort of lose this advantage by going to an E-house, but in a block building, you are going to have at least 30 inches. I believe that's correct for the NEC, and I hope somebody will correct me if I'm wrong, of working distance between the rear of that switchgear and the wall, at a bare minimum 30 inches. If the switchgear is front connected, then the gear no longer requires that clearance. So here's one solution, and there's a few manufacturers that make this type of gear, and this is really IEC gear that's been ANSIfied. And ANSIfied is my cute word for bringing IEC gear into the US and making the necessary modifications, if any, to test it to the NEMA standards. So you can see here the bottom is the cable connection compartment, and the middle portion here is the breaker compartment. And so obviously one limitation here is this is a one high design. There is no two high design for this particular manufacturer. It's a great design. This one happens to be arc resistant. There are some limitations, and one of those limitations is that this is bottom entry only. So you have to be willing to run all of the conduits underneath the building and through the concrete and that kind of thing. And there are several manufacturers who make this particular design. And so let's see what that does to our room. That reduces the footprint of the medium voltage switchgear greatly, even in a one high design. This is another option we've seen some manufacturers do. Basically, you have a medium voltage cable pull section in the front of the gear. So they're with each section, you're not saving any width because you have to have this pull section, and they're using a narrow design in this particular option, a 26-inch wide breaker and PTs, and then they're using a 19-inch pull section, if you will, and it's a good design. This is a wonderful design as well. This is a 26-inch wide design that's too high. This is rear connected, so you're not going to be able to use the front connected in this configuration. But and this slide is actually wrong. I apologize. This is limited to 15 kV and it's 2,000 amps. So the drawing that this came from, the manufacturer can do this up to 2,000 amps.
Okay. The feeders can be 2,000 amps as well there, Michael, at 26 wide?
I believe so. And so let's look at what's happened to our lineup. We've taken our old traditional one high metal-clad switchgear. It's 36 inches wide, one high, and usually that means the breakers in the bottom, the instruments, and the relays are on the top section. And we have compacted things all the way down to 130 inches of linear width, and the depth, being held constant. So that really has affected our room as well. I do want to point out up there that you do still need the 30 inches of clearance in the rear. This is another. It's becoming more and more popular, and I'm going to let Mike talk about this particular design. This is what we call switchover breaker. So Mike, take it away.
So this has all the advantages I previously mentioned associated with the 3-position isolation switch. where you now when you, whether you have a fixed mount breaker or you have a draw out breaker, you can isolate that breaker for maintenance purposes. And statistically speaking as well, you have the option now of of avoiding racking, whether it's remote racking, okay, or whether it's racking right in front. The fact is, racking is a mechanically complex operation, and your greatest risk of an arc flash event is while you're racking on. And although you can avoid damage to personnel with remote racking, that still doesn't obviate the obvious damage to the equipment should an arc flash event occur while racking. Should there be a mechanical misalignment or one of the finger springs break off during the racking operation. So the reality is, anytime you're racking on energized bus, it's a mechanically complex operation and the risks are high. Having the isolation switch avoids that, but most importantly, it avoids the necessity for racking for simple lockout tagout. So you open the switch up to isolate, you lock it out, and you no longer have the necessity to rack out the breaker. For a mechanically complex operation, again, in order to achieve lockout tagout requirements. And opening that switch and locking out takes merely a few seconds. And again, it's an arc rated switch, so it requires no PPE for that operation. So, numerous safety and maintainability advantages, in addition to the real estate savings, which Michael is doing such a good job of articulating in the presentation. Back to you, Michael.
That's great, Mike. Thank you. Okay, so hopefully we've opened your eyes to a couple ways to get creative with the medium voltage switchgear. Let's move on to the medium voltage motor control. Okay, so traditional medium voltage motor control is almost always 36 inches wide, one high. There are occasions, I'm told, where you can do a medium voltage contactor two high, up to a certain amount of amps and horsepower, but 36 inches, that's the standard. This is a company called EMIC. It's a really neat story. A gentleman purchased this company from Arriva 10 or 15 years ago, I believe, and has really taken it to new heights. And it's an old IEC style motor control design where the contactors are ABC front to rear. And there are a lot of paper mills out there that just that love this gear. And if you're looking for a reliable motor control across the line and save real estate, then this is a good answer. One thing that's very nice about these guys is they're here in Georgia, right down in good old Perry, Georgia. So they're a drive away. Here's another drawing of that same lineup. So again, one high starters, 12.6 inch sections. And I believe they are also arc resistant. So let's just look at our footprint and what we've done here. If you remember, we had 3 motors on our one line that were across the line. And so our standard, I believe a lot of people call it the amp guard gear. I think that's a Eaton or Cutler Hammer term. There's lots of other terms, but the standard across the line medium voltage starter is 36 inches wide. So we are left with a 108 inch lineup. And if we take another look at it and get a little bit creative and talk to the folks at EMIC, and now we're down to 12.8 inches per starter. And that still includes our protective relay of our choice. and contactor and fuses, and a non-load break disconnect switch. So what have we done to our room? We have significantly reduced our footprint over here in our medium voltage motor control. Okay, if you're going to talk about size, you have to have a conversation about UL 891 versus UL 1558. UL 1558 is the standard for low voltage draw out switchgear. UL 891 is a standard that it refers to front connected switchboards. Now, this is, some of you may be having deja vu because we just had a discussion about metal enclosed versus metal clad. These terms are absolutely analogous to the metal clad and metal enclosed, but this is in the low voltage world. So UL 1558 is to metal clad as UL 891 is to metal enclosed. There are very little rules for UL 891 regarding construction. It's mostly about testing. And in UL 1558, they're going to tell you exactly how to build the switchgear, where the barriers have to go, where the breaker goes, all of the temperature rise testing and that kind of thing. So here is a drawing of a typical UL 1558 piece of gear. And you'll see that I've highlighted a dimension over here to the right, which is 72.875 inches. And that is generally the depth, if not more, of a UL 1558 lineup at 480 volts. Here is a drawing of a typical front connected switchboard. In this case, it's a automatic transfer or automatic transfer board that starts a generator, but that doesn't really matter. The point is that it's 36 inches deep and it's front connected. So we've saved depth and we've also eliminated all those requirements for the rear clearances. In case some of you are wondering how it's connected, for this distribution part of the board, these are wireways. They become unbolted and the contractor will run wires from the bottom or top down this wireway to the breakers. Over here, these cabinets are hinged, and if you were to come up from the bottom, this door would open and the cables would come in the bottom and into the breaker here. Here's a link over here to the right for the full set of drawings if anyone wants to look at them. Okay. We used this trick on several projects. About 8 times out of 10, you will save linear width by rotating the core and coil assembly of the transformer 90 degrees. And this is usually in a dry type transformer. A dry type transformer, until you get to about 3,000 kVA, is longer than it is deep. So we've had customers come to us and say, I need absolutely every inch of room that I can get in the electrical room. I need to reduce the size of this e-house, that kind of thing. So we turn the transformer core and coil 90 degrees. Now it's ABC front to rear. And we put the temperature controls, of course, still on the new front of the transformer. And this is what that does for us, especially in applications where the UL is, the client is dead set on UL 1558 gear. It's going to be very, very deep anyway. Turn the transformer 90 degrees and you will save quite a bit of linear width, because then the transformer will be about as deep as the UL 1558 gear. Okay, here's one I've run across a few times now in the past couple of years. VFDs, in order to meet IEEE 519, usually require some sort of filter. And we, meaning Danfoss, and the other manufacturers like Yaskawa and I believe Eaton and Schneider, offer pre-packaged enclosed drives with a transformer, a reactor already installed into the cabinet that acts as a filter to try to get the total harmonic distortion to less than 5% and therefore meet IEEE 519. And this is how we do it. And there's a disadvantage to this. You're going to see exhaust and intake vents, and those require what? Clearance. So in addition to that, this setup is 39 inches wide. And so if we're paying $300 a square foot for a block building, or $150 for an e-house, this gets quite expensive. So here's a better way to do it. This is the drive, and this setup is 12.8 inches wide for the drive. And we have an active filter here that is 23.7 inches wide. I got that highlighted here. You may not be able to see that, but here's a better view of the active filter. It's 23.7 inches wide and 80.4 inches tall. And this filter will usually handle the harmonic correction for 3, 4, 5, 6 drives in a lineup. So instead of having to have this huge enclosure with a passive filter and that requires all of these clearances, we have several individual drives on their own, all being corrected by one active filter. And so here's an example. Let's say we have 5 motors on VFDs. We have a 400, a 300, or 2 300s and 2 175s, and we have to meet IEEE 519. Before, what we have here is a VFD, and it requires 24 inches of space. And when we've gotten a little creative and taken a closer look at it, now we have 5 drives that are coupled together and one active filter, reducing the harmonic distortion of all 5 of those drives. Okay. I'm a big fan of putting the transformer outside. I believe most of the data centers like Google and Facebook and QTS have resorted to putting transformers outside simply to reduce the building HVAC load. But there's some other reasons as well. Here's what happens to our room. Of course, our room shrinks. But what do we know about the secondary of the transformer? If any of you have been attending some of these webinars, you know that the secondary of the transformer is the highest available arc flash incident energy of any place on the electrical system. That 480 volt, which is probably, in this case, probably a 3,000 amp service, is going to have an enormous amount of arc flash incident energy. And if it's outside the room, that's a good thing, and we'll talk more about that in a second when Mike takes over. But so we reduced the footprint of the load. That's one reason to put a transformer outside. We reduce the HVAC load, and you know, add an arc quencher to the secondary of that transformer, which is what Mike has made his living doing, putting arc quenchers in the secondary of liquid-filled or cast coil transformers. Put an arc quencher in the secondary of that transformer, and now your electrical room requires no PPE. Here's a project where we got creative a couple years ago. Did a project with Siemens, and they decided to, hey, look, we can't afford the real estate to have a main breaker in the switchgear. We've got to have a main breaker. So where are we going to put it? Well, we configured the transformer bushings to for just the right dimensions, so that they would match virtually exactly to this fixed mounted UL 1066 power breaker, which acts as the main for this switchboard. It's really a nice way to save space and save dollars. And the transformer manufacturer put the breaker in the cabinet and attached the bus bars to the bottom of the breaker so that they could terminate secondary lugs to that breaker. All right, Mike, this is where you take over for a minute.
Got it. Okay. Do you have a graphic up there that you're bringing up, Michael? There we go. I do believe that secondary virtual mains, although they've been allowed by the National Electric Code since the late 1940s, so this is not a new solution, but it is a solution that has gained rapidly in popularity since the publication of NFPA 70 in 2004, and of course the 2009, 12, 15, 18, and 2021 editions. The reason for this is one, it's obviously safe space by eliminating a secondary physical main, okay, and replacing it with a secondary virtual main has space saving as well as safety benefits. So in this picture here, we could see from an arc flash mitigation point of view, if we don't want to use a secondary virtual main, if we have a physical main, right, our only choice, and not to make the entire lineup PPE category dangerous, meaning typically over 40 calories per centimeter squared, meaning no personal protective equipment is safe, is to physically segregate the feeder circuit from the main. And we can do that and connect with conduit, bus duct, or cable duct. But not only does it take, that's going in the exact opposite direction of Michael McClellan's excellent presentation today of how to save real estate in the electrical room, and particularly in new construction, real estate is very expensive. But more than that, with the requirements of NFPA 70E and lockout tagout, physical mains, if they're close coupled to the feeder, it aren't even a legitimate lockout tagout point, because if you're close coupled, you open the main, you lock it out, the line side of that main is still hot, it still has a very high arc flash incident energy, and therefore so does the rest of the lineup. So if you go to the next graphic, Michael. Michael, there we go. So this shows a typical physical main configuration. And I want to point out that the National Electric Code makes absolutely no distinction, okay, between a physical secondary main, okay, and a secondary virtual main, okay. Both are allowed, both have the exact same functionality and efficacy in terms of overcurrent protection. So in this case, with a Y secondary, we have to provide overcurrent protection within 10 feet of the transformer, and that's done, as you can see in this example, with a 2,000 amp main breaker. Now, a 2,000 amp main breaker typically would go in a 30-inch wide section, and so the elimination of that main breaker and replacing it with a secondary virtual main not only saves that real estate, okay, but it also makes for a safer system for all of the feeder breakers as well. So if we're close coupled here, this is both the main and the feeder in the same gear. In this example, the equipment would be 62 calories per centimeter squared, meaning no PPE is ever safe while that equipment is energized and at the IEEE 1584 18-inch working distance. So the alternative to this, the space-saving and safety benefit alternative, and next slide, please, Michael, is to implement a secondary virtual main. So we eliminate that 2,000 amp physical main, right? And we replace it with a set of CTs, one on each phase, an overcurrent protective relay, which trips the primary device. Now, clearly, in order to make this space-saving alternative work, you need to own the transformer. If the utility owns the transformer, this is not an option that can be implemented. So now we've eliminated a piece of hardware that we need to maintain. We've shrunk our real estate by at least 30 inches. Again, depending on the ampacity of the main itself, how much space you'll be saving. You'll always be saving some, but the larger the ampacity, the larger the transformer, the larger the secondary breaker, the more space you're going to save. And now we've moved our lockout tagout point for the substation to that primary device. And again, if that primary device is a switch over breaker, in this case, if we were to add a switch to this one line, you open the switch, you ground the switch, so it's a 3-position switch. So in a matter of 5 seconds, you've opened, you've grounded, you locked out, tag out. All you have to do now is verify absence of voltage and go to work. You've established an electrically safe and grounded working condition. Save yourself real estate, and usually save yourself a little bit of money, because that secondary main, which really serves no purpose in a world of NFPA 70E, if you own the transformer, has been eliminated. Back to you, Michael.
That's great, Mike. Thank you. Okay. Another space-saving design I've run across a few times, or an item that takes up a lot of space in an e-house or an electrical room, are the batteries. On the left is what I'm used to seeing when I walk into a battery room or a switchgear room. I see a rack of batteries and I see spill containment. And it usually takes up, 150 inches perhaps of linear space. And these are flooded batteries. And then there's a charger somewhere else. And this is, over to the right is a solution we've used lots of times over the past few years. And it's a battery, charger, and DC panel all integrated into one enclosure. So you've taken this 150 of linear inches of batteries, and you have consolidated all that into a say 36 or 40-inch wide enclosure that has the charger, batteries, and the DC panel pre-integrated, pre-tested into an enclosure. Very cost-saving, time-saving piece of equipment. Okay. So I guess I'm saying here, the best way to save room in an electrical room is to not have an electrical room. There are a lot of advantages to going to an e-house. Here's a typical example. This is a prefabricated electrical house made of metal interlocking panels, or it could be a welded seam building. And you see it has switchgear doors integrated onto the rear of this building, and that eliminates all of your requirements for those rear clearances that we discussed earlier. In this particular example, the customer, maybe this is going into a substation, looks like the customer's coming into this building from overhead. So there are overhead air insulated bushings integrated into this particular example. So what does the e-house do to our room? Well, it reduces the size even further because now we have these doors on the back of the house, and this is our access door. And now, whether we are front connected or rear connected, we have eliminated the need for the rear clearance, because basically what happens is the gear comes to the e-house manufacturer without doors on the rear, and it's integrated into the e-house, and then the e-house door becomes the switchgear door. There's a lot of reasons to go with an e-house. I could do an entire presentation, probably in 2 parts on the e-house, but I'm going to keep it simple for today. All of the labor to integrate all the switchgear, to test it, is at the e-house manufacturer. I don't know what they make these days, but the guys at the e-house manufacturer are probably $25 an hour. A contractor on site is $150 an hour. Anything that you can do in a factory environment is always cheaper and simpler than doing it on site. There are some tax advantages, or at least there were. I'm reasonably certain those still exist. I believe if a e-house is delivered on site, from a tax standpoint, it's treated as equipment versus a capital expense, and it can therefore be depreciated over a 5-year period instead of a 30-year. And there's no weather delays. There's a lot of projects that get delayed here in the South in the winter, because it rains so much. This is an e-house manufacturer that I've familiarized myself with, and they're right here in Georgia, just south of Atlanta. And that pays dividends, because you can drive to the e-house manufacturer and watch the gear being tested if you like, watch the control system being tested, or witness the testing of the protective relays. And it's nice to be able to drive to those kind of things versus having to fly. In addition, this particular e-house manufacturer has a unique design in which they're using a aluminum sheathing with some sort of core in it that has a very, very high R value, reduces the HVAC load. Geographically, this is kind of what's happening. If you purchase the electrical room that we just went over, we'd probably have transformers coming from Roanoke, Virginia. We may have a transformer or two coming from Chihuahua, Mexico, or Juarez, Mexico. We may have low voltage switchgear coming from Minneapolis, from States Electric, and we may have some medium voltage gear coming from Winneconne, Wisconsin. And we may have some low voltage drives coming from Rockford, Illinois. And all this would come to the e-house manufacturer in Fayetteville, where it would be integrated and tested. So looking back on our electrical room and our endeavor, how did we do? Did we save ourselves some width and therefore save us some dollars? Well, our medium voltage transformer disconnects, we went from 126 linear inches to 59 inches. On our medium voltage switchgear, on the option we chose, we went from 252 inches to 130 linear inches. And we saved quite a bit of space as well on the medium voltage motor control. Those 36 inches of amp guard contactors were going to cost us 108 inches of linear width. And we got that down all the way down to 36.9 inches. Did we save on-site money? Well, did we go with an e-house, or did we go with a block building and let the contractor put together the switchgear? It's important to realize that switchgear, all switchgear from all manufacturers, unless it's specified differently, comes in shipping splits. It comes in usually 2 sections of low voltage gear and usually 2 sections of medium voltage gear per shipping split. And this is a lot of time and effort for the contractor in the field, and he has that in his price to integrate it. That number is way less if it is integrated at an e-house manufacturer in a factory environment. Okay. Looks like we have some questions. Okay, our first question: would using an arc quencher save space and give location options versus the older technology mechanically vented switchgear? I guess, Mike, I'm gonna let you take that one if you're still on.
Okay. Yeah, I mean, an arc quencher is always going to take up a little real estate in your switchgear, so we don't make the lineup smaller, okay, by adding an arc quencher. Frequently, we can add an arc quencher without adding anything to the real estate because it isn't a very large device physically, either at low voltage or medium voltage. So we can keep the real estate the same. The advantage, of course, in the arc quencher is the safety of the equipment, because the addition of the arc quencher, I want to be clear, to any existing, okay, or new equipment lineup converts that lineup to be compliant with IEEE C37.20.7 for arc resistant switchgear or equipment, and is labeled as such. Okay? And that same benefit, as long as you extend the light sensor network to the downstream assets, that same arc resistant benefit is extended to those downstream variable frequency drives, motor control centers, and control panels, panel boards, anything that is fed from the distribution system. So good question. Thank you.
Okay, somebody has asked, what is the interrupting technology? Vacuum interrupter or air insulated switch? I believe this is referring to the HVLCC mechanism, and that is a SF6 interrupter. It's a hermetically sealed SF6 interrupter.
Yeah, and there's never been a leak in one of those SF6 switches. The actual, it's about 6 pounds per square inch of SF6, so it's like a flat bicycle tire. And because of that very low pressure, there's never been a problem with leaking, with tens of thousands of units installed globally in the field on that device.
Hey, Mike, isn't there this is Adam, I think, well, for one, you can do it fused or non-fused, so you can also get the fuse protection feature built into it. But I do believe that HVLCC mechanism is a little bit more limited from a KA standpoint than a traditional fuse disconnect switch. That might be the only one kind of clarification, but I can't remember if it's 31 and a half or 40 or.
Yeah, so it is limited compared to an air brake switch in terms of KA. It's limited to 40 KA, up through 15 kV. The switch itself is available all the way up through 34.5 kV applications. but it does have a lower interrupting rating, but I'll tell you what it does have. It has a higher mechanical rating. Most of those air switches are good before you need maintenance, right? For 100 mechanical operations or 10 load break. Whereas the LBS kit, what you call HVLCC mechanism, the Schneider electric switch, is 10 times that. So it's good for 1,000 mechanical operations and 100 load break operations. So in cases where it can be applied again within its withstand rating, it has a much better mechanical life than most of the air brake switches.
Yeah, agree. Yeah, just something to think about as people might be thinking. That HVLCC is one of my favorite things to use on a project. Just the only thing to know is, limitation is 40 kA. But if you need higher than that, there's other creative ways to save space, like Michael showed, the 26-inch wide breaker. We can go to a breaker design and get the higher kA capacity when that comes about.
Okay. Here's another question. Is the SPS HVLCC basically the equivalent of a EU RMU, ring main unit? I'm not familiar with that terminology. Are you, Mike?
Oh, yeah. Just because I've sold piles of them during my career working, and I've worked in 68 different countries other than the United States. So a ring main unit, which is sold by all three, by the way, of the major European manufacturers, Siemens, Schneider Electric, ABB, is a compact switching mechanism with SF6 all in one compact package. And to answer the question, yes, this is our to use, I actually like Michael McClown's terminology, our ANSIfied, okay, our North American, our ANSI IEEE implementation of ring main switching unit. Absolutely. It has the identical functionality. If you go back to the beginning of Michael's presentation, showing how those switches were put together.
Okay, great. Another question was, is there a need for a bus transition section between the mains and tie in the updated layout for the 15 kV gear? It's a good question, and I believe the answer is no. That's why I put the tie in a section on its own, so there would be room for that bus transition.
Yeah, that's right, Michael. You got that right. So yeah, that's traditionally how we would do it. And there are cases where we can put a main and tie in the same section. It just requires a lot more bus work in the rear. But you don't have to have just an independent standalone transition section.
Yeah, that's one advantage of, the manufacturers we represent. I think we all would agree that they're very, very competitive in price, but we still call them custom switchgear manufacturers because we don't sell things by catalog number. If you order switchgear from the 4 major manufacturers, which it's great gear, it's all wonderful. I'm not going to badmouth anyone, but the business model is to sell switchgear that everything has a catalog number. So Jake, for your question, if you purchased that gear from Eaton or one of the others, yes, you would need a bus transition section, because one division of the plant is not going to custom make a rear bus for gear coming from another portion of the plant. Whereas we are going to design the entire lineup to fit together.
Exactly. The other thing you won't typically find from any of the 4 major manufacturers of switchgear, global manufacturers, is hybrid switchgear. So if going back to one of Michael's earlier drawings, if you take a fixed mount isolation switch with integrated grounding and you combine that with metal-clad style construction, meaning you have a draw breaker below it, and you still have insulated bus and bus bushings between your sections, that doesn't qualify as metal-clad gear because it incorporates an element of metal enclosed as well. So it's really hybrid gear. It's metal-clad switch gear with some metal enclosed elements included in it. And it has many of the advantages of both construction. And that's not the type of safe, efficient, maintainable design that you can typically obtain from any of the major switchgear manufacturers.
That's great, Mike. Thank you. Our next question is, how difficult is it to maintain the smaller width gear? I'll paraphrase, especially if you're over 200 pounds. I guess what I would like to comment on is let's focus on the HVLCC switch, and that is a maintenance-free device. It is hermetically sealed, and all of the literature from the OEM manufacturer of that component, Schneider Electric, states such. It is a maintenance-free device. On a project, we did have a contractor comment, but you know, he was the type of guy who complained about everything, but putting in the phases run ABC front to back, and he did comment that it was challenging to connect the bottom cables to the C phase because you had to reach, your arm all the way back there. My comment to that is you only do it once for the life of the switchgear. So it's challenging, but certainly not impossible.
Yeah, I would add that in the answer to the question, I see the question here asked, what happens if you're a 6'2", 250-pound bub, I asked here, is that going to be a problem? And my answer to that would be when you're looking at compact switchgear, that it depends. If you're looking at metal enclosed gear that's fusible, the front to back configuration you mentioned, Michael, that could be a greater challenge for a large individual. But in general, compact gear, as a general rule, is easier to maintain no matter what your size. So if you're looking at a compact circuit breaker, for example, a Tavrita, the Arc Flash 12 millisecond clearing time circuit breaker in switchgear, that circuit breaker not only has a longer warranty and more mechanical operations than other popular vacuum breakers on the market, and not only does it save space, you could implement it in one of those 26-inch wide sections that Michael indicated, but it's half the size and a third the weight of a conventional medium voltage breaker. So regardless of how big or how little you are physically, working with that breaker, a conventional breaker, you need a crane, whereas one of these compact breakers, an individual can easily work and transport, remove and transport it around. So a lot of times when we improve our insulation systems, we make things smaller and the components smaller. It regardless of your size, becomes much easier to maintain. Good question.
That's great, Mike. Thank you.
Well, also, Michael, one thing I'll point out too, if it's just a switch, if we're building it, we can also have side access covers. That can be fleshed out during the design process if you want to have the ability to stand to the side and have an access cover on the side to do your cable terminations. Same thing on the switchgear, or we can make, you know, front and rear access panels to where you can access the rear. So there's a lot of creative things we can do with switchgear and metal enclosed fused switch construction to give you easy access for connecting the cables and maintainability. Just as long as we know you want that there, we can do it.
Great. For those of you that are multitasking, there is a poll up that just enables you to request more information on one of the subject matters that we discussed, just in case somebody's washing dishes while listening to this. Here's a good question. Are there any environmental issues in the USA with using SF6 switchgear versus vacuum bottles?
Can I fill that one, Michael?
Sure, Mike.
Okay. And the answer is there are no issues per se in terms of codes or standards, but there may be issues, of course, related to individual end user preference. Let's be clear, above 40 kV, it's all SF6. So if there are issues with SF6, the entire distribution system for the United States above 40 kV would have an issue. So the vast majority of circuit interrupters above 40,000 volts are based on SF6. To be clear, SF6 is a hydrocarbon. It is a hydrocarbon that is 6 times more concentrated than a hydrocarbon like Freon. And this is the reason over the last 20 years that vacuum breakers pulverized and virtually eliminated SF6 circuit breakers from the market. Okay? Is because of those concerns and SF6 leaking out of the vacuum bottles. The SF6 switch that Michael showed you today, though, is a very different technology. Rather than a high pressure SF6, because this switch, remember, it's an isolation switch. You can't trip it under fault conditions. It's load break, but you can't trip it under fault conditions. And because of that, the gas inside, okay, is again only 6 PSI. There's tens of thousands of applications. There's never been a leak. So the bottom line is there's no logical reason why it might be an issue, but for some people, when it's under 40 kV, they hear the words SF6. There could be personal preference issues, but certainly no technical, rational reason to have an objection to SF6 in North America when it comes to this particular switch that Michael showed.
Great. Here's another, this is a good question here. Doesn't the internal sheet metal barrier inside switchgear make each vertical section independent as far as arc flash goes? Meaning the high arc flash value on the transformer secondary only affects the vertical section, not the whole gear. Sounds like a question for you, Mike.
Sure, and the answer to that is, if it has been, you cannot determine that through empirical means. The challenge of an arc flash event, particularly since in virtually all cases on the unprotected secondary of a transformer bus, we're talking about an arc flash incident energy which is greater than, and frequently substantially greater than, 40 calories per centimeter squared at the IEEE 1584 working distance. That being the case, yes, you can construct a barrier, but you can't just construct a barrier and assume, okay, that it will not allow the arc flash to propagate. So you must create a design, okay, and then verify the arc resistance of that design, okay, within specific parameters and the maximum interrupting rating of the equipment at a high power test lab. Because what you find in switchgear is not only do you have barriers, but there's cutouts in the barriers and bushings in the barriers that allow bus to pass through, for example. And this is a key point that I would want you to remember. Just as electricity follows all paths in a shock event, but prefers low impedance paths, so in an arc flash event, the rapid expansion of the plasma during an explosion follows low air pressure paths. So if you're in one cubicle and that pressure is rapidly expanding, any holes, any gaps, any weaknesses in the structure are immediately sought out in the rapid propagation of that pressure expansion, which we perceive as an explosion. So the answer is yes, it's possible to construct switchgear this way. That is how mechanically vented IEEE C37.20.7 equipment is constructed and tested, but it's very expensive, and it can't be just determined empirically. It has to be validated through high power test lab testing, which most custom equipment configurations are not. Good question. Excellent question. Thank you.
Here's another good one. This is a gentleman who has some SF6 110 kV breakers, and they leak, and he has to refill them. Do these medium voltage SF6 breakers have to be periodically recharged? Adam, you've sold the most of these. I mean, you had any complaints?
Michael, give me that question again.
Have you had any complaints from the end users that you sold the HVLC C switch to about leaking SF6?
No, not a single one.
But this question, the question as he phrased it though, was not for medium voltage, Michael. He asked a question for high voltage, 110 kV breakers, right? And those breakers, unlike the SF6, are high pressure SF6. And if there's issues with the gasketing, they can be subject to leaking. And of course, for any type of breaker like that, we generally recommend a pressure monitor to monitor the SF6 inside the device. It's completely different than the low pressure switch, again, that Adam and Michael are talking about here, which is, again, only pressurized to 6 PSI. That's why there's never been a leak. Unless you run a fork truck into it or physically damage it, again, tens of thousands of units in the field without a single leak. Good question.
Yeah, I think the other item to consider there is those SF6 110 kV breakers they're metal, they're welded. This we're talking about a hermetically sealed enclosure that is molded. I'm not going to use the word plastic, so let's use epoxy or cycloaliphatic. And with a molded device, you are going to have a better seal.
Michael, there seems to be a number of questions about that 3-position SF6 switch with the integrated grounding feature. I've already sent you in your email a separate presentation which details that switch technically quite well. And of course, if anyone is interested, if you contact Michael McClellan or anyone at L3 after the presentation, they would be happy to send you the additional technical details on that switch. The presentation today, by necessity, was focused on reducing real estate, so it made just cursory mention, really, of the technical features associated with that device. If you are interested in additional information, please let Michael or any L3 person know.
Well, but yeah, based on the responses in the poll, I think we're going to set up a webinar just to discuss that switch, probably week after next. So We have another question here. Are any temperature controls included in the battery, the integrated battery assembly cabinet you showed? Gas sensors may also make sense. Yes, absolutely. There are temperature controls. There's absolutely nothing that kills a battery faster than heat. So yes, gas sensors, I think I should comment that that integrated battery enclosure system is only for VRLA batteries. Is that correct, Adam?
Somewhat for that type design where it's got the drawers that pull out so you can do maintenance on the different drawers of the battery system. Yeah, that would be VRLA batteries. But we do have the ability to put standard flooded lead acid or NiCad batteries in an enclosure as well. Naturally, it's going to get a little bit bigger. That's the neat thing about the VRLA batteries is it keeps the footprint down. It's what every UPS manufacturer uses typically in their integrated battery solutions in their UPSs. So, but we can do NiCad and flooded lead acid within an enclosure as well. Just actually the enclosure is going to get a little bit bigger when we do that.
Adam, this is Mike Vukovic. I could just one quick question of you. What is the comparative life of the VRLAs versus a conventional lead acid or selenium battery?
Typically 20-year life for all of them. There are some 10-year life batteries out there, which is no good, but typically for the applications we work on, we utilize a 20-year life battery.
Thank you.
Okay. That is all the time we have. Thank you so much for the questions. And I think we do have a couple unanswered questions, and I'll be getting back to you guys via email. Thank you again. Stay safe. Hope to see you at the next L3 Levine Electronics and Electrics COVID webinar.